I'm Marc Ritter. Thank you for the nice introduction and also for inviting me to this conference. So what I will be talking about is a bit more general than what I put on the schedule, which is new algorithms and also libraries that implement them. And I will also showcase some applications of these. And the work that I present here is mainly based on these two papers that, well, we put out some time ago. So, I mean, I will go through it very briefly because I guess everyone is very familiar with this stuff. But the setting I'm working in, yes. I see, okay. I can be on this side. So, okay, the setting I'm working in is the function representation setting. So yesterday we already heard there are two possible sources, thank you, of where you would get a tensor train from. And here, what I'm doing is I have a function that may be very complicated and be dependent on many variables. And so if I do something very naive, like just a Cartesian discretized grid, Cartesian product of discretized grids, then I will be very unhappy because that will be very expensive to represent for that. So we discretize the function somehow into a tensor and then factorize it into a tensor train. And as we heard many times before at this conference, this will hopefully get me from an exponential scaling to some linear scaling in L, which is the number of indices here, provided that this bond dimension chi, which you find here on this bond, is not large in some sense. So this is like the intuitive picture, right? Okay, and the first step here, the discretization, what I will be using in this talk is always the quantics representation. So the quantics representation is the simple idea that as the tensor indices, you can use the binary digits of your variable x. So if x goes from 0 to 1, you can discretize it on 2 to the r points with r bits. And then each of these bits corresponds to a certain length scale. And so that way you get a tensor where each index represents a length scale, and then you can TCI it. And if the sort of the entanglement between the length scales is not large, then you get a small bond dimension. So this is all the intuitive picture. And a simple example for this is an exponential that just factorizes right away if you put this binary representation in the exponent, which is why you get a bond dimension of 1 for an exponential and a bond dimension of n for a sum of n exponentials. And you can generalize this pretty straightforwardly to multivariate functions where you apply the representation to each variable separately. And then you get sort of, again, this hierarchy of scales from large scales to small scales. And to get this, I reorder the indices according to the length scale. So instead of having the bits for x separately and then the bits for y, I reorder them such that the largest bits, largest length scales in each variable come first and the smallest length scales come last. And then you can TCI, or you can factorize this in two different ways, which I call the interleaved and fused representations. But yeah, so this that detail that you can ask me about if you want. Okay, so now we have discretized the function. So here comes what I actually want to talk about, which is, okay, how do we factorize this into a tensor train? I will talk about the tensor cross interpolation algorithm, which skips this explicit representation as a tensor, which we want to skip because this may be way too large to fit into memory, right? And so the algorithm that was already introduced yesterday or presented yesterday by Sebastianov is this two-side tensor cross interpolation, which is a sweeping algorithm in like a DMRG-like fashion, where you take out a small tensor where two of the indices are left free to take all of the values, but all of the other indices are restricted to take values only from a small subset of their possible values. And I call these I and j. And so this tensor is much smaller than the full tensor, and so we can represent it explicitly in our memory, factorize it in some way. And then these factors here give me the tensors that I put back into the tensor train. And the factorization that we use here is the cross-interpolation, matrix cross-interpolation factorization, where you take out a bunch of columns and a bunch of rows and put them in a column matrix, a row matrix, and pivot matrix, which you invert. And this gives you the three tensors that you later put into the tensor chain, and that's what we call a local update. So that gives you an algorithm that scales with chi cubed d squared and in runtime, and chi squared d squared, and always linear in L in memory. So there are a few things to be said about that. So that's like the sort of default version that was introduced in the first papers. And what you would do there is you would only ever add one pivot in each local update. And these added pivots, so the matrix cross interpolation, would tell you which columns and rows are important. And this gives you an updated index set of I and j here, I here and j here, which you then use in the subsequent local updates on the neighboring bonds, right? And so this works, but in the spirit of what Marcus told us yesterday, why does it work, right? And so the reason that it works must be that the local update actually improves globally our approximation. But why is that the case? And that is the case because of something called the CI canonical form and some properties of it. So yeah, bear with me for a moment. This is a bit technical. So the CI canonical form says that our tensor chain is in a very specific gauge. And that gauge is in the way that each of the tensors that make up my tensor chain, these T and P tensors, are actually slices of my full tensor. And this gives us, on one hand, the sampling property, so that I only need to sample very few elements from my full tensor, because if you take some linear combinations out of the full tensor, then you will need the whole tensor to calculate that, right? So what I do here is I define slices on the full tensor by defining these index sets I and j that limit the values of the indices here. And then the p's and t's are defined as f called on each combination of the elements of I and j. So an example would be down here. If you have a tensor with 5 legs and you look at P3, for example, P3 is given by I3 and J4, and if it has these elements, the matrix P3 is just f called on each combination of the elements of I3 and J4, right? And so there's a one-to-one correspondence between the elements within our tensors and the index sets here. So optimizing my tensor chain means optimizing my index sets. Okay. So what we actually do in the what we actually do in this local update is we optimize our index sets, and our tensors are updated according to this definition and the new index set, right? And why is this now an improvement? So for that, we have to look at what the global error does and what the local error does. In a sense, so I talk about the global error as the difference between my full tensor that I want to approximate and the tensor chain. And the local error is the error that we actually improve in our local update, right? And so if we look at these differences, we can find correspondences between the upper and the lower row. So if we just look at the global error on this index set, yeah, which is what we actually have access to in the local update, then we can find that, well, this is actually the definition of the tensor down here, right? So these two are equal, exactly. If we look at these two, the only difference is that we have added some tails to the left and the right. And so, okay, you can figure this out. You don't have to read through it right now. But the gist of it is that if you look at these tails on some particular subset here, these i's and j's, then they collapse to deltas of these inputs in blue and these outputs in red, right? And this happens if the nesting condition is given, which means that these index sets have some particular structure where the longer index sets, and so where the shorter index sets for shorter tails are actually nested within the longer index sets, right? And so if that is given, we get out these deltas, and so we can replace our tails by deltas, and then these two become equal, right? And so this is why the TCI algorithm works, because the global error and the local error on the subspace are actually equal exactly identical. And so by doing a local update that optimizes the local error, we are also decreasing the global error on that subspace, right? But that also, yeah, okay, so this is what I just said. But we can also, with our understanding of why it works, now deviate from this recipe and introduce some variants of the algorithm that do things differently, but still work. And so I call this TCI1 and TCI2. So TCI1 would be like the conventional thing that was introduced yesterday, and these are our new elements that we added. And these all solve specific problems. So one thing that happens very often in this TCI1 algorithm is when you calculate your local update, you need to calculate the inverse of the pivot matrix, and that becomes unstable. Actually, it's the usual case in my experience for applications that this inverse becomes unstable. And there's a way to calculate it using an LU decomposition that remains stable always. The reason why it becomes unstable is also related to only ever adding one pivot each. So if you have ever added one pivot, and imagine that pivot, so if you imagine that pivot has a small absolute value, and then later the sampling algorithm discovers that the function has much larger structures somewhere else, then you get large and small values in the same matrix, and just intuitively this very quickly or very often leads to very different singular values, which then make the inversion unstable. And so we have a variant of the algorithm that allows removing pivots if they are not helpful. And then you can also optimize the pivot search, but this is a bit technical. So I will run you through these in a bit more detail now. So the LU decomposition is a decomposition of a matrix into a lower and an upper triangular matrix, and you probably know that maybe from your undergrad. And what we do here, and this idea is due to Uriel, by the way, here is we want to calculate the LU decomposition because, as we will see soon, it will also give us the information about rows and what rows and columns are important. But we want to decompose this matrix in such a way that we maybe don't need to sample more values of the matrix than we need. And so that's why we do it in a partial rank revealing way. And so we build up our lower and upper triangular matrix column by column and row by row until we have reached an approximation of the matrix that's good within our tolerance. And the way to do this is by a Gaussian elimination algorithm, which finds a new pivot. I will tell you soon how that works. Then swaps rows and columns such that they are added to this upper triangle and the lower triangle, and then does the Gaussian elimination step, which is actually what gives the Gaussian elimination algorithm its name. And you may have seen this algorithm also in your undergrad in a different formulation, probably for solving linear equations. Yes, you have a question. Yeah, so if you if you decompose the entire matrix, this is full rank revealing LU. But so if you iterate this until the next pivot that you find is smaller than your tolerance, then and then you stop, then you don't need to find any more values of your matrix. So that's why it's partial rank revealing. And it's rank revealing because if your matrix A has a particular rank and you have already added that many columns and rows, then you perfectly approximate the entire matrix. So then this will be equal, and that's why it's rank revealing. And it's, of course, in practice you would introduce a certain tolerance because, okay, at least me, I usually don't care about approximating it exactly, and so. In that case, you rank reveal it up to that tolerance, right? Yes.
The partial is not related to the pivoting.
Yeah. So the
truncated decomposition.
Yes. So what Jason said is that it's full pivoting, but it's truncated at a certain rank or at a certain number of rows and columns chi here. But yeah, about the pivoting, I will talk in a moment because there are variants to it. But yeah, it's full pivoting in the sense that you do swap rows and columns, and usually like the partial pivoting is only swapping one of them. Yes. Okay. Any more questions about this? Okay. Okay, that's because if you compare a CI factorization with an LU factorization, you can actually see that all the elements that you need for the CI factorization are also given by the LU factorization. So this row tells us how you get the matrices that you need for the CI factorization. But even more importantly, these combinations of column matrix times pivot matrix inverse and pivot matrix inverse times row matrix that we need for our CI decomposition, those are given by a combination of a triangular matrix times triangular matrix inverse, which can be calculated very stably because this is a triangular matrix. So this is a system of equations that you can just solve by back substitution or forward substitution, depends on which one, right? Does that answer your question? Okay, yeah, sorry. Okay, so what we do here is we have a matrix that we want to approximate, right? And if you compare the CI factorization to the left and the LU factorization of the same matrix to the right, you can see that if you take slices of all three sides of this approximate equation, basically, you see that these elements that you need for the CI factorization exactly correspond to some of the L times U, LDU products by taking submatrices here, right? So you can take out the same submatrix here, and then you see that parts correspond to each other. And then you can also see that these combinations that can be potentially numerically unstable can be calculated in a stable way because you have this triangle matrix here where you invert.
So you do not compute the inverse of A11, right?
Yes.
Combine A11 with the left or right.
So this inverse we never compute explicitly because we actually never need it explicitly. We only ever need a combination of another matrix times this matrix inverse. Oh, sorry, I can't hear.
Can you just speak louder because others also would like to hear what
you just want the columns times some matrix.
Yes, so you want only the columns times pivot matrix inverse.
Never want A11 inverse.
Yeah, or A11 inverse times row matrix. So yeah, so that's okay. What you see here, like these squares turn, like these diamonds are the pivot matrix inverse, right? But you never need them. You only ever need them in combination with one of these squares, which is the row or the column matrix. Does it make sense?
I guess I'm not totally convinced you couldn't do it with the QR, rank revealing QR.
Okay. Yeah. So one way you can solve this.
This is what we started with, but this is extremely stable.
Yeah.
And slightly cheaper.
Yeah.
Yeah,
so you can actually, what you can do is you can calculate this with a trick by taking a combination matrix and then calculating a QR of it and so on. But this is even more stable than that. And as I said, that relies on this triangular matrix property. Yeah. Okay, I mean, we can discuss later if you want. Yeah. Okay, so yeah.
There's another position that is it's called complete orthogonal position, which is you hit basically QR from both sides and do pivoting. Have you thought of that?
I can't say I'm not familiar with the decomposition, so
It's also called UTV decomposition, I think.
Okay.
So it's yeah, we can discuss after.
We can discuss after that. That maybe like goes into too much detail for right now. Yeah. Okay. So yeah, as I said, what happens very often when you use the CI factorization in the context of tensor cross interpolation, right, to approximate a tensor, what happens very often is that this A11 matrix has very different magnitude values in it, and so A11 inverse becomes unstable, and you don't want to do it explicitly, and that's also why this LU decomposition is more stable. And the one thing I didn't tell you about yet is, okay, how do I actually find a pivot? And so, first of all, what is a good pivot? And this is a bit of the physicist intuitive way, right? So intuitively, what we want to optimize in our local update is this difference between the exact matrix and the approximation to the matrix, which is this combination. And this combination is also known as the Schur complement. And you can intuitively think about it as if you want to eliminate if you want to minimize the error, what you can do is iteratively that you eliminate the maximum error at each step. So you find out, okay, where is this difference maximal? You take that as the new pivot, update your difference, and then take again the maximum. So this is sort of a greedy algorithm to minimize your error. What would actually be, well, quasi-optimal, that's shown in this paper, is this Maxwell principle that was also talked about yesterday, which is that this is optimal or quasi-optimal if the determinant of P is maximal. But maximizing the determinant is a hard problem, right? Because we are using it in the context of the tensor cross interpolation algorithm, what we really want is something that's good enough. We don't really need the optimum, because globally over iterations, the good enough will still lead to convergence. Right? So the simplest algorithm to do this is, well, just generate this combination and look for a maximum and do this iteratively until you have found enough rows and columns to satisfy your error tolerance. A slightly more clever way to do it is to do the so-called rook search, which, again, we don't really need the optimum. We just need something that's good enough. And so what you can do is you put a chess rook into your matrix at a random point, and then you do a scan over the row to find the maximum in the row. You put the chess rook there, and then you scan the column that it's now in to find where it's maximal. And you do that a few iterations, usually 3-5 iterations are enough, and you find something for much cheaper, because this search is now not m times n, but only scales with the maximum of the two. And then there's a variant called block rook search, which basically does rook search on multiple pivots simultaneously, but yeah, that's also a bit technical, so you can ask me about it if you want. All right. So now I have explained to you what the LU is. I haven't yet explained to you how this accumulate versus reset works. And as I said before, well, the LU decomposition generates our CI decomposition very stably. And there's actually, you don't have to use it in a way where you just add one pivot each time, but you can actually just give the LU decomposition the freedom to generate new pivots in each of the local updates. And this will slightly violate your nesting conditions. So your correspondence of global and local error is not guaranteed anymore. But in practice, this works. And because in practice, the nesting condition is usually only slightly violated. It is much more stable. Because you have the freedom of removing these very small pivots that make your matrix inverse unstable. And these small pivots don't add much to your approximation anyway. So that's what we usually do. And I would actually recommend using these three as the default and only switching over to the left column if you need it, right? And so in this way, instead of having chi-sweeps that add one pivot each, you have just a few sweeps. In practice, it's usually something around 5 or 3 to 5. And they add or remove something that's smaller or equal than chi pivots each. And so in each sweep, you can sort of double your bond, up to double your bond dimension, and be satisfied with that. Yeah. All right. So this algorithm is one of the ways of generating TCI, but it still has some problems that are unrelated to this numerical stability, which is that, okay, sorry, let me talk about something else first. So I talked about the CI canonical form, so some of its uses are, for example, the interpolation property. But one thing I also want to point out is that this pivot information that you get from it is also useful because you can just reuse the pivots. So if you have multiple functions and you know they have a similar structure, then using the pivots that you got from one function approximation and just putting it to approximate another function can be already very good, or can be at least a very good starting point for doing a TCI optimization. And we can obtain such tensor trains either from tensor cross interpolation. There's also a one-side and zero-side variant, but I won't talk about that. And there's a way to CI canonicalize tensor trains, which means you give me an arbitrary tensor train, an arbitrary MPS, an arbitrary gauge, and I can tell you what are the pivots that correspond to that. And the way that works is by 3 sweeps. So what you need to do is each of these decompositions is, again, a CI composition or this LU decomposition that we use to indirectly generate the CI decomposition. And starting from the left, because we know the values of sigma 1, we know what the rows of the first matrix mean. So if we do this decomposition, we know what values are in this index set. And if we now go to the second side, we can do this decomposition again. And because we know both of the inputs of this matrix, we now know what is in I2, and so on and so forth. And so we can generate all the I index sets, the row index sets. In the backward sweep, we do the same except flip left to right, and we generate all the J sets. And then that's not obvious, but we need a third sweep to restore the full nesting condition because it might be broken here. And so that way, from an arbitrary tensor train, you can generate a tensor train in CI canonical gauge. And this gives you pivot information, and then you can use it for everything you want, right, with a normal CI canonical tensor train. Yeah, and then there's this global pivots point here that I didn't talk about yet. And this is here to fix a certain problem that was also mentioned yesterday, which is that sometimes some functions have regions that are sort of disconnected by gaps. And what that means is the TCI will not discover structures, so this TCI algorithm will not discover structures if they are not reachable by these local updates. So say we have a pivot 1, 1, 1, 1, 1. These here are all reachable by a local update because during our two-side optimization, we optimize always on pairs of indices, right? But if all of these don't have any interesting structure, and the interesting structure is then hidden in these locations, for example, these are not reachable by local updates because you cannot reach them by updating a neighboring pair of indices, right? And so here you have to help the TCI algorithm. So the first thing here has 3 indices that you need to change at the same time. A two-side update can't do that. This here has 2 indices that you have to change at the same time, but they are not adjacent. A two-side update cannot do that. And so the way you can help TCI here is by adding global pivots. And this is really simple. So if you know that at 1, 2, 3, 4, 5, there's interesting structure, what you can do is you can just like generate these substrings. So from the first to the fourth one, and here again from the back. And you can add them to these local index sets that define what your P&T matrices are, and then update your P matrices and T tensors, of course, right? And that way, you have a tensor train that now has 1 point of the new structure. And then if you run optimization from there, then it will discover all the structures. So one example for that is if you have a function that has only a 1 at 0, 0, 0, 0, and 1, 1, 1, 1, 1, and you only give it one of these as a starting point, then it will not be able to discover the second one unless you also give it the second one as a global pivot, right? And so this fixes some of these ergodicity problems that are very similar to these Monte Carlo ergodicity problems. All right. Yes, and you can even do it automatically by just searching globally through the space, and I believe it's on one of the posters, by generating a random point and doing a rook search globally for a maximum of the function. And by the way, maximums of your function are very good starting points for TCI optimization. So how much time do I have left? Okay, yeah. Okay, so and then there are some libraries. Including questions. Okay, well then I have 5 minutes. Okay. Okay, so we have some libraries. So these are Julia libraries maintained by Hiroshi and myself. And the original implementation is based on the XFAC libraries that are being maintained here by Uriel and by Xavier and by his group. Okay, unfortunately, they are not yet in this form, but soon. But so this is sort of the structure. So there's a part that deals with tensor trains, and there's a part that deals with quantics, with conversion to and from quantics. And then there are some add-on pieces that are new. So if you are implementing anything based on quantics tensor trains, you can sort of pick and combine all of these libraries, and they are made to work together, right? And the new parts that are new, so that are not given in this talk, are on 2 posters. So first of all, Simone is working on parallelizing all of this stuff, both contractions and TCI, and he has something about that on his poster. And then there are ideas about patching. That means having different patches of your functions and tensor trains that only discretize one patch, and Gianluca has a poster about that. Okay, one very nice thing, or maybe let me skip that. So there's a quantics Fourier transform, but it's also implemented and it's very nice, but I won't talk about it for lack of time. So one of the projects that we applied this to is a Parquet equation solver with these wonderful collaborators. And what the Parquet equations are a set of self-consistent equations, the most expensive of which are the beta-salpeter equations, which look like this. And they're expensive because the objects in these equations are multi-dimensional functions that have structures at different parts, and it's hard to predict where those are, and so on. So this is a place where you can use quantics tensor trains to compress your structure. And in fact, the beta-salpeter equation can then be reformulated by introducing these dummy variables omega into 2 sums, the blue and the red one. And you always have an output connected to an input, sort of. So if you generate quantics tensor trains of each of these 3 objects, this beta-salpeter equation looks like 2 MPO contractions in series. So runtime and memory of this will scale linearly in L, which is the resolution or the number of frequency points that we have, right? Provided, of course, that chi is not too large. This should give us a major runtime and memory saving. And by the way, there's also a poster by Samuel on doing that more efficiently with more including momentum dependence. And so we benchmarked this first on a Hubbard atom as a proof of principle, and it turns out it works very well. So with a bond dimension of around 200 and then 10 to 11 bits of resolution, you get convergence in your Parquet solver that really is the same as your conventional one. So there's no additional error due to your QTT approximations that somehow accumulates or something like that. The self-consistency iteration really works as well. The major savings here are in memory cost, which for the Hubbard atom, you can still do this without quantics tensor trains. And for our other benchmark, which is a single impurity Anderson model, you can also do it. But the argument here is that this is a proof of principle and can very easily generalize this to having momentum dependence in there or multiple orbitals without blowing up your memory, which would happen if you didn't use any compressed representation, right? So that's just a very quick rundown. Ask me if it's unclear. And there's another poster by Markus Frankenbach about combining a local vertex with from DMFT as an input instead of approximating some part of the equations here. Which is also very nice because you can get this input already in QTT form, which you can then plug into the rest of the code. Okay, with that, let me briefly summarize. So I told you something about innovations in the TCI algorithms, the LU and rook pivoting, for example, the CI canonicalization. I told you about the libraries. I didn't tell you about this for lack of time, but I did tell you about the QTT Parquet project, and thank you for your attention. And I'm open to questions. And also, I want to thank the collaborators. Sorry.
Open to questions, comments?
Hi.
Hi.
Doesn't hear, I think, or yeah, it does. Yeah, it's my hearing then. It's you talked about one-side TCI and two-side TCI.
Yes.
Is it still relevant for some problem to use one-side TCI with respect to the two-side?
Okay, so here what you want from two-side TCI is, so one of the nice features of it is that it dynamically adjusts this bond dimension, right? If you do a one-side update, this cannot really happen, so it cannot increase the bond dimension. And so if you just approximate a function from nothing, basically, you don't already have a QTT approximation, but you want to approximate a function, then usually I would use two-side TCI. So one-side TCI is cheaper, so it scales better, right? And so there are some algorithms where you might want to use it to, for example, recompress something, or where you already have an idea of what the ranks should be and stuff like that, or you have some other way of generating what you
want. Recompressing something means that you run TCI2 and then you run TCI1, or?
It means, so for example, I mean, TCI2 is not the only way you can get a tensor train, right? So for example, in this QTT Parquet scheme, right, I get a new tensor train from contracting two tensor trains. And if you have an algorithm like that, for example, you can use that. Yeah.
Thank you.
But, and one thing I forgot, it's also, if you, for example, reuse pivot information from some other function, right, you can run cheaper one-side TCIs, for example, to remove pivots that are sort of redundant, right? And I would actually recommend doing that.
Sorry, I'm not sure why is a canonical formulation needed in your
okay, so
mathematically.
Okay, so it's necessary for this local update to make sense. So yeah. Okay, what we want to do is okay, let's see here maybe. So what we want to do is we want to get an approximation of the full tensor, right? But this full tensor in many cases is much too large. So I never want to generate explicitly the full tensor. I only want it formally as a function that I can call to get elements of the tensor. But what I want to do is I want to build this approximation from as few elements as possible of the tensor, okay? And so if you imagine introducing some like unitary rotations or something like that, right? Like if you imagine rotating bases in these on these sigmas, then you need to sample multiple elements of the full tensor to generate one element of your rotated basis. And so that's one reason why you don't want to do that. And then if you rotate even like globally, then you need to actually sample the full tensor to generate one tensor of your basis transforms, one element of your basis transform tensor, right? So this you should never do this. And then even local rotations, you need to generate like the full local space to get one element of your tensor in the rotated space. Yeah.
So does canonical form also help with to preserve the nesting condition?
Well, the nesting condition only makes sense to talk about in the canonical form, right? Because here you have the notion that your elements are given by these index sets, right? So it's not like a basis, but it's really index sets. So the basis only sort of has a single one somewhere, right? And then the nesting condition means that these index sets have some relation to each other. Yeah, and you can only talk about it if you actually have index sets.
Okay, thank you. Thank you so much.
Yes.
Thank you for very interesting talk. Can you go back to the slide when you compare?
Here, yes.
Yeah. So there is no reference, so I'm not really sure what TCI1 refers to. But if you refer to algorithms developed in our group, we never really proposed to use full pivot search at two-site level.
Okay.
It was always an option, but we were using the rook pivoting and the combination of rook pivoting and the random search, just like you did.
Okay.
So there are obviously there are differences between technologies, but if we allow the full search, this would expand our complexity quite dramatically beyond the linear in dimension and linear in mode size, and that's unacceptable. Of course, we understand it very well. So yeah, other than that, yeah, thank you very much. The Maxwell, which you refer to also on other, but it's 1997. It's not 2011.
Oh, okay. Yeah.
It's 15 years before.
My
that.
apologies for.
No, it's fine. Yeah. It's fine. Thank you very much once again.
So, yeah,
sorry
maybe
for the.
You can give me the correct reference for the Maxwell.
It's easy to find. Yeah,
okay.
yeah. I will show you. Yeah, but it's just to put things in historical perspective. Yeah, it's a little bit older than 10 years now. It's almost 30 years.
Okay, old. So even for the CI.
Yeah, tensor cross interpolation for matrices was around in Tertishnikov's groups from 1997.
Okay.
Yeah, and many ideas that we are using now are actually just high-dimensional versions of the old ideas, which are possible due to the very good properties of tensor train format, because it's really a generalization of matrix techniques.
Yes. Yeah. So actually, even some of the innovations here with the LU and CI, this we discovered later. Some like for matrices, some of this is already given in some of the papers, but it's like the combinations are new.
Yeah. A lot of matrix ideas are directly applicable to tensor case, of course. For example, the LU and CI superposition that you make here, it was always well understood that you don't things that you explain are always well understood. We just never bothered to maybe explain it properly, but it was very well understood that inverse matrix is not something you need an application of this to a factor and so on. So but I think it's very important to emphasize them. So I really think it's an important part of the work to show intrinsics of the technology. And thank you very much for doing this. And sorry for this being more a comment than a question.
No, it's
Any other comment or a question? Yeah.
I'm curious about your point of the slight violation of the nesting condition.
Yes. Okay.
And this, so the nesting condition gives you all these nice properties. Does a slight violation mean all these properties immediately formally go out of the window, or can you recover some of that?
Okay. Maybe so this is where I talk about the nesting, right? And so for okay, what this bottom line tells you, right, is that if you have multiple blue inputs sigma and a red output b, then this collapses to a delta of all the inputs and all the outputs, like, permuted possibly by this index set, if the nesting condition holds for all the substrings, right? So, but that also means that for different pivots or for different inputs and outputs, you get this delta or you don't get it, depending on whether the nesting condition is fulfilled for this particular pivot, right? So, and so by slight violation, I mean that for most pivots, right, the nesting condition is still satisfied and we have removed some of them. And so for them, it's violated on some of these substrings, right? And so then for most of the subspace, it still holds that this is exactly equal and not for strictly everything, right? And so what that does in practice is that we find, okay, the optimization still works. It's still good enough, but probably if someone tried something similar to what we saw yesterday with converging stuff to 10 to the minus 100 or something like that, there I would think you would probably find some difficulties with that. Yeah.
Maybe last question.
Yeah, just a quick comment. So if you really want full nesting, after doing this scheme where you slightly violate it, you can do a one-side sweep and restore it.
Yes.
Right. So
exactly. So yeah, you can always restore the nesting condition, and for our applications, or at least, or I think for most physics applications, probably it's actually advantageous to allow it to violate the nesting in favor of more numerical stability.
Okay, any other comment or question? If not, let's thank the speaker.
Thank you.